In the vehicle routing problem, VRP, for urban solid waste collection, a bi-objective optimization model is developed to incorporate the visual attraction of routes, focusing on the compactness of routes. This criterion, often overlooked in logistics distribution literature, significantly impacts practical routing plan implementation. The bi-objective model minimizes travel times and maximizes route compactness, subject to time constraints. To solve this multi-objective problem, the authors employed two exact solution methods: the weighted sum method and the augmented epsilon constraint method. The weighted sum method assigns weights to each objective function, while the augmented epsilon constraint method transforms the bi-objective problem into a single objective problem by adding an epsilon constraint to the objective function. Experimental tests on small-scale instances evaluate the trade-off relationship between both objectives and assess the computational efficiency of the solution methods. The results demonstrate the importance of considering route compactness in solid waste collection problems, as it directly affects the practical implementation of routing plans. The author's approach introduces a novel criterion to the VRP literature, highlighting the significance of route compactness in urban solid waste collection. The experimental results provide valuable insights into the trade-off between travel times and route compactness, enabling decision-makers to balance these competing objectives in real-world applications. This research has implications for developing more efficient and effective distribution plans in urban solid waste collection and other logistics distribution contexts where route compactness is a critical factor. Optimizing vehicle routing problems with time constraints. A bi-objective model for visually appealing routes. In logistics transportation planning, vehicle routing problems, VRPs, are crucial decision-making processes that aim to design optimal routes for a fleet of vehicles to serve a set of customers. Conventional optimization criteria focus on objective measures such as minimizing transportation costs, distances, or travel times. However, another important optimization criterion is the visual attractiveness of routes, characterized by compactness, confinement to a bounded geographical region, and an approximately circular shape. This bi-objective model optimizes vehicle routing problems with time constraints, considering the minimization of travel times and route compactness. The significance of this research lies in its practical implementation in real-world scenarios, such as urban solid waste collection. The model's development contributes to the creation of visually appealing distribution plans, which have been identified as a tool for reducing operational costs in transportation logistics. The mathematical formulation of the problem is presented in Section 2, while Section 3 discusses the experimentation and results on realistic instances of the waste management system of Bahia Blanca. The results provide insights into the relationship between travel time and route compactness, as well as the computational efficiency of the solution methods used. The trade-offs between the two objectives are assessed, highlighting the importance of balancing travel time and route compactness in logistics transportation planning. The study's findings have implications for the development of more efficient and effective transportation systems, with potential applications in various industries. Future work includes exploring the integration of additional optimization criteria and the development of more sophisticated solution methods. The compact vehicle routing problem with time constraints is a complex optimization challenge that involves balancing route efficiency with visual attractiveness. Compactness, a key measure of visual appeal, has been defined and categorized in various ways across literature. Constantino et al. 2015 identified three types of compactness measures, while others have proposed defining compactness based on travel times, Euclidean distances, and proximity between customers. Recent studies, such as Linfati et al. 2022, and Kilby and Popescu, 2021, have applied compactness metrics to optimize route planning. However, incorporating compactness into optimization processes can lead to nonlinear models, making them computationally challenging. As a result, most existing approaches are heuristic in nature. This study proposes a compactness calculation adapted from Poot et al. 2002, and formalizes the vehicle routing problem with a time limit through a mathematical programming model. The model comprises sets, parameters, and variables, including the set of vehicle routes, points generating demands, vehicle capacity, time limit, volume of product to be collected, travel time, service time, and time for unloading the accumulated product at the depot. The mathematical formulation of the compact vehicle routing problem aims to minimize the total distance traveled by vehicles while satisfying time constraints and compactness requirements. The model's nonlinear nature is addressed through the use of heuristics, enabling the solution of large-scale problems. By integrating compactness into the vehicle routing problem, this study contributes to the development of more efficient and visually appealing route planning strategies. The mathematical model for the problem is formulated using previously defined sets, parameters, and variables. The objective is to minimize two key metrics: total travel distance and compactness measure. Total travel distance is calculated as the sum of distances between nodes I and j, weighted by the binary variable xijk, which indicates whether the vehicle travels from node I to node j during route k. Compactness measure is calculated as the sum of distances between nodes I and j, weighted by the binary variable zij, which indicates whether nodes I and j are part of route k. The model's constraints are presented in equations 3 to 10. These constraints ensure that each node is visited only once, except for the depot node 0, and that each route can start from the depot at most once. They also ensure the conservation of flow within the route, preventing the formation of subtours and limiting the time per route to the maximum time established by the working day. Additionally, the constraints guarantee that nodes I and j are part of the same route k if and only if there exists a node h such that xhik and xhjk are both 1. The variables x, z, u, and v are defined as binary and continuous variables, respectively, and are subject to the constraints presented in equations 3 to 10. The model's objective is to find the optimal solution that minimizes both the total travel distance and compactness measure, while satisfying all constraints. Researchers introduce a binary variable xijk to indicate whether nodes I and j are part of the same route k, taking a value of 1 if they are and 0 otherwise. To linearize the nonlinear product of variables in equation 10, they apply the linearization methodology proposed by Glover, 1984. Preliminary computational experimentation is conducted on small-sized test instances based on realistic instances of the municipal solid waste system of Bahia Blanca, Argentina, developed in previous fieldwork. Cavalin et al., 2020. Two multi-objective approaches are employed, the normalized weighted sum and the augmented epsilon constraint method, to study their characteristics. Rossit et al., 2017. The model is implemented using the Pyomo optimization package in a Python environment, with the Gurobi solver version 10.0.2 used to solve the resulting mathematical programming problem. Experiments are executed on a system with Intel Xeon Silver 4214 processors, 32.0 GB of RAM, and a Windows 10 Pro operating system. In each instance, the number of efficient solutions to obtain is set to 10. With a time limit of 1,200 seconds given to Gurobi to return the best solution obtained. None of the executions reach the optimal solution, which is expected given the n-fard nature of the vehicle routing problem, VRP. Figure 1 presents the Pareto front of the proposed instance with 9 nodes, showcasing the non-dominated route that provides a good trade-off between objectives. The augmented epsilon constraint method obtains 7 non-dominated solutions in 8,400 seconds, while the weighted sum approach obtains 6 non-dominated solutions in 12,000 seconds. The results demonstrate a clear trade-off among objectives, with solutions that have good performance in terms of travel time exhibiting poor results in terms of compactness and vice versa. The augmented epsilon constraint method outperforms the weighted sum approach in terms of finding solutions in the non-convex regions of the Pareto front, and achieves a better usage of computational resources. The bijobjective approach is validated, as the results confirm the existence of a trade-off between objectives. This research focuses on optimizing vehicle routing problems, subject to capacity and total route time constraints. The primary objective is to minimize travel time and enhance route compactness. A novel bijobjective mathematical formulation for the vehicle routing problem, VRP, with time limits has been developed, which can be linearized. Computational experiments on test instances reveal a clear trade-off between minimizing travel times and maximizing route compactness, indicating these goals are inherently conflicting. The study provides decision-makers with a set of non-dominated solutions, allowing them to select the most suitable solution based on their specific scenario. Two traditional exact multi-objective approaches were compared: the weighted sum and the epsilon constraint methods. The epsilon constraint method outperforms the weighted sum in identifying solutions in non-convex regions of the Pareto front. Furthermore, the augmented epsilon constraint method optimizes computational resource utilization. Future research directions include expanding computational experiments with diverse instances to better assess compactness objectives. Heuristic approaches could be developed to address the trade-off between travel times and compactness in real-world scenarios.